This video is to run through the proportion sampling distribution simulator. So we are now imagining that we are collecting samples and we want to look at the potential sample proportions that we could get for various true population proportions. So everything we're thinking right now is related to the binomial distribution, where here's our probability of success or the true proportion. N is our sample size, and then the number of samples to draw. We're just going to do one at a time for right now, and then we'll explain what's happening. So if my sample size were small, like 10, and I were to draw a sample, so this sample, we got 4 out of 10 successes. If I draw another one, we got 2 at 4 successes. And we got another one. There we go. So now we took 4 samples, 3 of them came out to 40%, one of them came out to 60%. And if I continue to draw one sample at a time, eventually this distribution would start to fill out. So let's do 100. So we're taking a sample size 10. So the options for possible p-hat values are 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, or 100. If we do 100 samples, we can see that, oh, it looks roughly normal. You can overlay a normal curve and see that, yeah, this one actually looks not too bad. Keep in mind, we have 10 times 0.5, which is n times p is equal to 5. So it's kind of right at the border for what we would consider to be normal. But what happens if I increase my sample size to 20? And we'll still leave the true proportion of success at 50%, and we'll just go straight to drawing 100. Let's actually do 1,000 so we can kind of look straight at the final answer or final distribution. All right, so what we can see here is right at the center of this distribution is 50%. That looks like it happened the most often. And as we get further away, the probabilities are getting a little bit smaller. What we can notice is since our sample size is 20, it's possible now that we could get 15%, 20%, 25, 30, 35. So there's a little bit more subtlety in our values along our horizontal axis. We can have more possible p-hat values. If I draw 1,000 different samples, it's going to start looking normal-ish. Again, it's better now that our sample size is larger. But of course, we want to have larger samples if we can. All right, so let's change this probability now to be 0.25, and let's make our sample size 10. We'll draw 1,000 samples again. So something we can note is when we multiply n times p, this does not meet the criteria for using the normal approximation. And when I overlay this normal curve, we can see how much error there is, right? It's almost impossible for us to have gotten anything between 0 and 1%. And we can probably guess that it's possible if I took samples that we might have 8%, 10%. But because we don't have n times p bigger than or equal to 5, you can see that there's a large amount of error if we tried to use this normal distribution. Right, well, essentially what we're doing is we're trying to approximate those bars using this red curve. And we can see that there's quite a bit of error right now. If we instead increase our sample size to 100, note this now means that all of our p-hat values are going to be in increments of 1%. If I had 20 people, 20 successes, I would have a 20% sample proportion. If I had 21 successes, I had a 21% sample proportion. So as my sample size increases, the possibilities for p-hat is going to get larger and larger. It's going to be closer and closer to a continuous distribution. Let's do another 1,000 and just see. You can see that there is still some error, but it's getting much, much smaller. Let's change our sample size to 200. Let's draw 5,000 samples just so that we can see. Give it just a second. And then I'll also show us these summary statistics so we can note what the central limit theorem tells us about these distributions. So what we are again doing is approximating all of our simulated data with that smooth red curve. And there's a little bit of error. This one might actually have a decent amount of error, but we're going to get fairly similar distributions. It is definitely approximately normal, looks roughly symmetrical. Things aren't perfect, but the real world never is. So the central limit theorem tells us that as long as we have independent trials and a sufficiently large sample size, which is n times p bigger than or equal to 10, or n times 1 minus p bigger than or equal to 10, or some variation of that, you might see a couple other versions of that criteria, then the central limit theorem tells us that the distribution of p hats, possible sample proportions, is going to be approximately normal with a mean of the true population proportion. So I don't want the sample data, I want the summary stats. So this is saying that the middle of this distribution should be approximately 0.25. Here, our mean is exactly 0.25. It also tells us that the distribution of p hat values, well, so it has a mean of p, and it will have a standard deviation of p times 1 minus p divided by the sample size all under the square root. So we are taking the square root of 0.25 times 0.75 divided by 300. Was that our sample size? Was 200. My apologies. 200. And we get 0.0318. This has a standard deviation of 0.0309. So pretty close. If we were to approximate our simulated data with the normal distribution, we would be pretty close. Our values are fairly accurate. And of course, the larger our sample size gets, the more accurate our results are going to be. Hopefully that made a little bit of sense to you. When you start doing your central limit theorem homework, what we're essentially trying to do is say, let's ignore simulating thousands of trials. Let's just use this red approximation. Central limit theorem tells us that this red approximation is going to be pretty close. So as long as we meet the criteria, we can use this normal distribution centered at p with a standard deviation of p times 1 minus p over n all under the square root. And then we can use that normal distribution to find the probabilities that we are looking for. As always, let me know if you have questions, comments, concerns. Otherwise, I'll see you next time.